Warning: engineering content. Few minutes of engineering. Composition and hydration mechanisms of cement. Ordinary Portland cement is chemically composed of 4 vital oxides: calcium oxide, silicon dioxide, aluminum oxide, iron oxide, and various minor oxides such as sulfate. It is of a major importance that the chemical composition of cement is adequate for proper strength gain, workability properties, and durability properties of a mixture. Portland cement gains its strength through chemical reactions between the cement powder and water, which is known as hydration. The hydration process and the reactions during this process are better apprehended by understanding first the chemical composition of cement. The typical chemical composition range of oxides in ordinary Portland cement by weight is as follows. Calcium oxide ranges between 61 and 67%, silicon dioxide ranges between 19 and 23%, aluminum oxide ranges between 2.5 and 6%, ferric oxide ranges between 0 and 6%, and sulfur oxide ranges between 1.5 and 4.5%. The source of these oxides can be related to the raw materials used in the manufacturing process of cement, where limestone is the main source of calcium oxides, and clay is the main source of both silicon dioxide and aluminum oxides, with iron oxides as its impurities. The sulfate is sourced from the gypsum added to the clinker and not from the clinker's composition itself. Thereby, the chemical composition of clinker mainly sets the properties of the final cement product, which in turn determines the type of cement. Clinker is composed of 4 major compounds, produced from the chemical reactions between oxides during clinkering: dicalcium silicate C2S, tricalcium silicate C3S, tricalcium aluminate C3A, and tetracalcium aluminoferrite C4AF. The typical chemical composition range of compounds in ordinary Portland cement by weight is as follows. Dicalcium silicate ranges between 45 and 75%, tricalcium silicate ranges between 7 and 32%, tricalcium aluminate ranges between 0 and 13%, tetracalcium aluminoferrite ranges between 0 and 18%, and gypsum ranges between 2 and 10%. During the cement hydration, a series of chemical reactions, mostly exothermic, occur between cement and water to form the binding material. The first phenomenon occurs almost instantly when water is added, where some of the clinker sulfates and gypsum dissolve to form a sulfate alkaline solution. Afterwards, a series of reactions occur, starting with the most reactive mineral, tricalcium aluminate, where it reacts with water to form an aluminate-rich gel. This gel then reacts with sulfates to form ettringite crystals. The reaction of tricalcium aluminate generates high heat, but only for a short period of time, followed by several hours of relatively lower heat in the induction period. Tricalcium aluminate reacts with gypsum and water to produce ettringite and heat. After the induction period of the previous reaction, tricalcium silicate starts reacting to produce calcium silicate hydrate gel and calcium hydroxide, where tricalcium silicate reacts with water to produce calcium silicate hydrate gel, calcium hydroxide, and heat. Once gypsum is depleted due to the first reaction, the ettringite becomes unstable and starts reacting with the remaining tricalcium aluminate to produce monosulfate aluminate hydrate crystals, where tricalcium aluminate reacts with ettringite and water to produce monosulfate aluminate hydrate. The dicalcium silicate also reacts forming calcium silicate hydrate gel and calcium hydroxide, where dicalcium silicate reacts with water to produce calcium silicate hydrate, calcium hydroxide, and heat. Tetracalcium aluminoferrite undertakes 2 subsequent reactions with gypsum. First, ferrite reacts with gypsum to form alumina hydroxides, ettringite, and lime, where ferrite reacts with gypsum and water to produce ferric aluminum hydroxide and lime. The ferrite then also reacts with the ettringite produced previously, to produce complex compounds, that only fill voids and do not contribute to strength development of concrete, where ferrite reacts with ettringite, lime, and water to produce complex compounds. The calcium hydroxide produced by the reaction of dicalcium and tricalcium silicates reacts with amorphous silica, in the presence of poxolinic materials which are rich in this form of silica, to produce additional calcium silicate hydrate gel, where calcium hydroxide reacts with silicic acid to produce calcium silicate hydrate gel. This reaction is known as the poxolinic reaction.